go to Harvard to meet Nima Arkani-Hamed, an innovative physicist linking theory and experiment. I hear Nima embodies the excitement of this grand quest to dig into deep reality. You'll have to deal with the uncertainty principle, perhaps as part of the history of the quantum. Nima, how can we understand quantum theory?
In the late 1800s, we had two basic kinds of phenomenon that we'd seen in nature. Things like light and sound waves and other excitations of different media were described by waves, but things like billiard balls and, well, they didn't have cars, but if they had cars and other things were described as particles. Having these two different kinds of descriptions for phenomenon in nature started leading to some confusion. What people realized in the early part of the 20th century was that these two different things that were being described by classical physics, wave-like property on one hand and particle-like properties on the other, were, in the end of the day, all actually describing particles, but particles that don't move according to the laws of classical mechanics, but move instead according to the laws of quantum mechanics, which are very, very different than the classical laws that govern particles. For example, there was the famous uncertainty principle that said that while in the world of classical physics we associate the movement of a particle through space and time by specifying its position and its velocity at any given point, that we can't in fact specify the position and the velocity to infinite accuracy, and that if we know the position very well, we don't know the velocity very well, and vice versa. And all of this happened in conjunction with the realization that there's a new fundamental constant of nature, Planck's constant, which determined when classical approximations to the real underlying quantum physics was good and when that classical approximation broke down.
Now today we know that from this there's a large number of observations which we know to be true but would seem counterintuitive to our normal macroscopic lives. Particles entangled, tunneling effects where things seem to jump from one place to the other, and this seems to be impossible, but it is real.
It is absolutely real, and one of the unfortunate things about the way sometimes quantum mechanics is described is that there's an awful lot of mysticism associated with it, and uncertainty means that we can't be sure of anything, and maybe consciousness has something to do with the way the world is, and there's an awful lot of nonsense said about quantum mechanics, whereas in fact quantum mechanics is responsible for the absolute stability of everything we're made of atoms, for example.
Because the electrons can't occupy the same position.
Right. I mean, there was this old classical picture that an atom was like a little solar system with an electron orbiting around nucleus. And there were a variety of problems with that picture. One of them was that the electrons would quickly lose energy and spiral into the nucleus, and atoms would be completely unstable. And another one, a related one, is that even if you ignored that problem, you could imagine lots of different solar systems with lots of different distances, and why were all the atoms identical? Why is everything's made out of the same stuff? And both of these mysteries were solved by quantum mechanics with the realization that it was impossible for the electron to fall into the nucleus, because if it did, you would know both where it was and how quickly it was moving at the same time. And the uncertainty principle tells you that that's not possible.
So the uncertainty principle actually creates stability and absolute confidence.
Exactly. The uncertainty principle, far from introducing all kinds of fuzzy garbage, actually allows things to be stable and is responsible for all the gross properties of matter.
Atoms are not little solar systems. Little solar systems would be unstable. Only the uncertainty principle can create stability. Only because it's impossible to know the precise location and velocity of a particle, that's why atoms do not collapse. Wow. Yet, it sounds, well, too perfect? Too pat? Dare I say, too simple? There must be problems lurking somewhere. And I know just who's ready to reveal them. Lee Smolin, who has very controversial ideas about fundamental physics, which many of his colleagues don't like, which is why I should get to him. Lee's at the Perimeter Institute in Canada, but I find him in San Francisco and arrange to meet.
Lee, everybody talks about quantum mechanics, particularly what you call the foundations of quantum mechanics, relationship between quantum mechanics and general relativity. How can we begin to understand these fundamental problems?
One way to say it is that if you think that physics is supposed to give you a picture of reality independent of us, that tells you in every experiment exactly what's happening and why, which is what Einstein and everybody before Einstein thought physics was about, quantum mechanics doesn't do that. Quantum mechanics talks in terms of probabilities, and not even probabilities, some things prior to probabilities. If you scatter two particles off of each other, quantum mechanics doesn't tell you what's happening in an individual event. It tells you in a class of events what are the probabilities for different outcomes. Right. Einstein
Never liked that.
Never liked that. Schrödinger, Derbroglie, these were sort of half the founders of the subject, thought that certainly it works. It gives correct predictions as far as it's been tested. It is the basis of more and more technology. It's extraordinarily successful, but they didn't believe it, and many of us still don't believe it. It was controversial in the 1930s, and it's been controversial since. If you talk to different of us, there's some people who have bought the whole thing, which means that they have found a way of thinking and a way of talking that accommodates the weirdness of quantum mechanics.
Yeah, but no experimental evidence has contradicted it.
Sure, but the controversy remains. Some of us continue to think that it's a good tool, it's a good bookkeeping advice, it's a good predictive device, but it's not a fundamental theory, because a fundamental theory should describe what's happening in detail in each experiment. Einstein never bought it as a fundamental theory, Schrödinger never bought it, Derbroglie, many others, and I've never been able to buy it. Now maybe I'm dumb.
Well, I think it's dumb. I think it's a prejudice, because a probabilistic way of looking at a world being all smeared in some way, is uncomfortable in our modern way of thinking. But if no experimental data contradicts it, it looks pretty impressive.
It is pretty impressive, and the key thing that we've learned is that any theory that goes beyond quantum mechanics, that gives a deeper explanation, a deeper description, has to be fundamentally non-local. This is the spooky action and distance that Einstein talked about.
What does that mean?
It means that if you have an atom in an excited state and it decays and spits out two photons, that the state of those two photons remains what we call entangled. And that means that if I make a measurement on this one, and I make a measurement on this one, the probabilities for the outcome of this measurement depend on which measurement I choose to make over here.
Even though the distance between them could be vastly greater than the speed of light could travel.
Yes, and that's really, that experiment has been done. Newtonian physics worked and works, and it's our understanding of why these bridges stay up and why the water is different from the air and so forth, but it's fundamentally misconstrued. It's fundamentally wrong, totally wrong when it comes to a description of nature. So there's no problem in my mind with quantum mechanics working very well, but being totally wrong.
And working at a certain level.
Yes, yeah. Now, where you have to believe that, if you believe it's wrong, you have to believe that there's a crunch somewhere. Okay. One place I believe the crunch is likely to be is in cosmology. That is, we use quantum theory to study systems which are tiny compared to the universe as a whole. Okay. Some of us, and I certainly am guilty of this, have the pretension to study this subject of quantum cosmology, where we try to put the description of cosmology in the language of quantum mechanics. So we talk about the quantum state of the universe. Okay. My bet is that that's completely wrong. that at some point between our laboratory and the universe as a whole, quantum mechanics breaks down.
What's the alternative?
Old hypothesis, one of the oldest hypotheses in the subject, is that when you include quantum mechanics together with general relativity, the singularity goes away, and there is a time before the Big Bang singularity. That there was a universe before the Big Bang, and that rather than having to talk about the initial conditions of the universe as the explanation for why everything is the way it is, one has to talk about how the universe passed through this event. What was before the Big Bang? Because what was before the Big Bang evolved to become this very, very dense state, which then began to expand, which made everything. So if you like, you push the explanation back, and maybe that's a good thing, maybe that's a bad thing, but it's a scientific question.
Quantum mechanics working very well, but being totally wrong? Quantum cosmology, the quantum state of the entire universe? My head is spinning. Talk about an uncertainty principle. That describes me. How to make sense of all this? I go to MIT to see a pioneer in quantum computing, Seth Lloyd, who uses the weirdness of the quantum to make radically powerful computers. I know Seth. Can he help? We meet in his lab. Seth, how can I begin to understand this weirdness of quantum theory?
Well, maybe you shouldn't even try. Nobody understands it. That's the way I feel about it. You know, I've studied this for years. I did my master's degree at Cambridge in philosophy of science, studying quantum mechanics, trying to understand why it was that, that I can have an electron that's both here and there at the same time. Forget about it. I never understood it. But however, you can, if you try, you can become more comfortable with it over time. So, one way to become more comfortable, unfortunately, is to learn the math behind quantum theory, because there's a very nice, straightforward mathematical background behind quantum theory, and the math says, hey, electron here, electron there at the same time, no problem. Okay? Well, unfortunately, if we want to do this intuitively, then it's tough. Our intuitions, our poor classical intuitions, are never going to understand this. In fact, I think that our intuition for quantum theory gets ruined at a very early age, around 3 months. Because it's at 3 months, when they do studies on infant cognition, it's around 3 months that babies start to believe in the permanence of objects, right? Peekaboo,
Yeah,
right? You play peekaboo with a kid who's younger than 3 months old, it's no fun, because you go like this, and they're like, oh, daddy's gone, right? After 3 months, they're like, they know you're there. But their intuition for quantum mechanics has now been ruined. So I think you should just forget about getting a good intuition about it.
Okay, all right.
Yeah. In fact, even many famous Nobel Prize winners have people who got their Nobel Prizes in quantum mechanics, like Einstein, right? Einstein, he didn't really even believe in quantum mechanics at some level.
Right.
I think that's because, quantum mechanics is just intrinsically counterintuitive. And if you're Einstein, you believe your intuition, right? His intuition says, hey, this quantum mechanics stuff is weird, I don't believe it, right? So he didn't believe it, even though he got his Nobel Prize for the photoelectric effect.
I think Feynman said something like, if you think you understand quantum theory, that proves that you don't.
Yeah. Niels Bohr said, I can't say it in Danish, that would be more impressive sounding. He said, anybody who thinks they can contemplate quantum mechanics without getting dizzy hasn't properly understood it. Small ones, like these quantum computers right here. This one has photonic acid.
This stuff's hard. I've struggled. But to know reality, I must deal with the quantum.